Hello and welcome to the first session of the Theory and Applications of Network Coding course. My name is Alex Prinsen. I'm with Texas A&M University. So the main idea of network coding is to allow intermediate nodes on the network, intermediate routers and switches, to mix packets. What we allow is for intermediate node, if it receives two different packets from maybe different interfaces or maybe the same interface, the intermediate node can actually mix those packets together, so in some way combine those packets or compute some function of those two packets and forward this function on one of the outgoing links. As we'll see, this new capability significantly changes what can be done in the network in terms of improving performance, security, and so forth. And this course's main idea is to explore this new capability and see what we can do and how we can construct good codes and how we can take advantage of this. And in general, what we exploit is a new flexibility that we have with information flow as opposed to regular commodity flow. So in information flow, if you have a packets and digital packet, we can duplicate this packet and send two copies over outgoing links. And with network coding, we can also combine two different packets and compute some new function, for example, just a bitwise exclusive for of those two packets, and send this new packets over one of the outgoing links of the network. And of course, this cannot be done with traditional network. It changes the game, and the purpose of this course is to explore what can be gained by this, and again, trying to take advantage of these new capabilities. So the area started by seminal paper by Alswede, Hein, Lee, and in Young in 2000. And as we see the 15 years of research, we have a lot of new results. And in this course, we will cover a lot of techniques that was developed during those 15 years, and also we'll explore directions for new research. This is still new emerging areas with a lot of open problems and a lot of room for additional research. So with traditional paradigm, with traditional routers and switches, intermediate nodes, they just forward packets. For example, this node will receive packet A and can forward it to one of the outgoing links, the same with packet B. And with traditional approach, the packets follow some paths for unicast. So for example, we have a central server and we want to forward packets from a sender to a receiver. So those packets will follow a unicast path. With multicast, the packets can be sent along a multicast tree. So in this case, we'll have multiple receivers. And to optimize performance, we can forward those packets along this tree. So each intermediate node will duplicate packets, and they will be forwarded along nodes of this tree, and each terminal will receive them. With network coding, the topology will change, and we will see that topology will not necessarily be a path for unicast and tree for multicast. By mixing those packets together, they will follow a more complicated paths and subgraphs. So network coding, again, the idea is that intermediate nodes can compute new functions. So those functions in general can be nonlinear functions. Of course, for practical purposes, we will be focusing on linear functions. In most general case, the node can compute function of two or more packets and just forward it. In practical applications, we use finite fields. And a field in general is a set of elements with two operations, addition and multiplication. And each result of addition and multiplications of those two elements will produce another element of the same field. In network coding, we're using a Galois field, which is a finite. A set of elements in this field is finite. So finite field is very useful for practical purposes because each element of the finite field can be represented with the same number of bits. So we'll not get a result which is not representable with the same number of bits as two original packets. We will have a short reminder about finite fields in following lectures. And, for practical purpose, again, it's not only we will use Galois fields, but usually we'll have an extension field of 2. So the finite field that we will use will include 2 to the n elements. That again, each element in this field will be represented exactly with 2 to the with n elements. So once we're doing this, so each element again is a member of this field. Each packet will be element of this finite field, and each coefficient will also be element of those fields. So with linear network coding, we will take two packets and we'll multiply them. So we'll take packets A and B, we'll multiply packet A by coefficients beta 1, packet B with coefficients beta 2, then we'll add them together, and the result will be forwarded on one of the outgoing links. Another packet, we can use a different coefficients. For example, we can use beta 3, so we'll multiply A by beta 3, B by beta 4, and forward results on one of the outgoing field. And again, if you're working on those fields, the result will be element of the same field, so it will be represented by the same number of packets. So those are linear codes that we'll be using. In practice, we will use this encoding over a symbols rather than a packet. So a packet will include a large number of symbols. For example, here we'll have red packets, and each and as this red packets will include a large number, and it can be hundreds of those symbols. And blue packets also will include a large number of symbols, and each symbols can be 1 byte, 8 bits, or 2 bytes, 16 bits long. So this way, those operations are not overly complicated and can be easily implemented in software or hardware. And also, as we'll see later, the overhead of doing this is lower when the fundamental symbols are smaller. So then the operation will multiply each symbol by the same coefficients on the red packet. For example, beta 1, we will multiply each of those red packets, red symbols by beta 1, multiply all of those blue symbols by beta 2, and add them together as kind of pairwise addition, and then get a purple packet which is including again on 700 those small symbols. So the coding will be done on symbol level rather than a packet level, and it's this way the coding will be more practical. So let's look on advantages that can be offered by this new paradigm of network coding. And for this purposes, we will look on this network which is called a butterfly network. And this butterfly network was presented in the original paper of network coding. So in this butterfly network, if you look on the left, right, so we have a source node S, and we have two terminal T1 and T2. And source wants to send data and wants to multicast data to those two terminals. So we want to send packets that can be decodable by both T1 and T2. And suppose that each link can transmit only one packet or message per time unit. And we want to send as many messages as we can. So it's easy to verify that if we don't use network coding, we can send at most one message per time unit. And in this case, these messages will be forwarded, as mentioned before, over a multicast tree. So this is a red message, right? So if you send this message over those links, so the message will be delivered by both T1 and T2. And this is just one possible tree. There are many others, but any tree that we use, we can see that we cannot send another message. So once we use this red tree, right, it uses all the those red links, and those red links will prevent us from sending any other link messages to T1, right? So we'll see that we try to send another message, will not get to T1 because this is this bottleneck link in the middle prevents from us from sending any other packet to T1. We can do a little bit better with using traditional techniques by splitting packets into smaller packets, right? So instead of sending those packets, right, big packets, right, that each link can transmit only one big packet, suppose that we can split those big packets into smaller size packets. So instead of one bit packet, we can send two smaller size packets, right? So for example, here we have one smaller size packet, which is a green packet, right? And those green packets are sent over green links. Then we have red packet, and then we have blue packet. Now, since we divided those big packets into smaller size packets, each link now can transmit two smaller size packets, not three, but just two, right? Because initially it was able to send one big packet. Now it's split into two smaller size packets, and each link can transmit up to two. And we'll see that what we have here, we're using three trees, and each link cannot be used by more than two trees. And which is so we satisfy this constraint in terms of link capacity. And we see that we have three of those trees, so one green, one blue, and one red. And in total, we can send three half-size packet, so our rate is 1.5 messages per time unit. So in this case, we'll see that it's basically the maximum number of information that we can send. We cannot send more, right? Again, it can be easily verified in this example. But we will see in the future that we can prove actually for this smaller example that it's not possible to do any more with using traditional approaches. And let's see what we can do by using network coding. So with network coding, we can actually send 2 messages per time unit. And this can be done in the following way. So we'll send M1 over these red links. We can send M2 over those blue links. And in the middle, what we can do to deal with this bottleneck link, we can mix those 2 packets together. So in the intermediate node, we can mix M1 and M2 and send this coded packet over those purple links. Now we need to verify, of course, that each terminal can decode both M1 and M2. So from point of view of terminal T1, we can terminal 1 receives M1 over this link and receives this coded packet over this purple link. So now it receives M1 and M1 exclusive for M2. So in this case, a symbol is just a single bit, and coding operation is just bitwise exclusive for of those 2 messages. If we get M1, we get M1 XOR M2, so we can get, by using XOR operation, we can decode both M1 and M2. And the same for terminal T2, again, so we receive M2. Okay, so we receive M2 over this link. We also receive M1 plus M2 over this purple link, so based on this we can decode M2 and M1. So everybody receives both messages, and we'll see that in this case both terminal T1 and T2 can decode both messages M1 and M2, so our throughput is 2. And we don't even need to divide those messages to smaller size messages. And we see that again, as this advantage of using network coding, we can overcome this limitation we will overcome this bottleneck link in the middle. And now we can send a larger number of messages to both terminal T1 and T2. Again, this is just a demonstration of additional capabilities that is provided by the network coding technique. So let's see additional advantages that can be obtained in wireless network coding. So suppose again we have a very simple setting in which we have 2 wireless nodes and we have 1 relay node. And suppose those wireless nodes, they cannot talk directly to each other, they can only communicate through a relay. So suppose again that node number 1 wants to send red message to node number 2, and node number 2 wants to send blue message to node number 1. So with traditional approaches, we need 4 transmissions. So node number 1 will send message A to the relay node, and node number 2 will send message B to the relay node, and then in the second phase, relay node will send message B to node number 1 and will send message A to node number 2. So we have 4 transmissions. So with network coding, we can do much lower number of transmission because in the second phase, so in the first phase will be the same. So we'll send message A, both nodes will send message A to the relay node. So we'll have 2 transmission. And the second phase, the relay node can just transmit a combination of A plus B, and it can broadcast a combination of A plus B to 2 nodes. And then with 1 transmission, we can satisfy 2 nodes, again, because node number 1 already knows A, so it's a red packet, so it can get A plus B, it can decode from this broadcast, right? So it can decode B, the message it actually needs, the blue message. It already has message B, so it again receives A plus B, and then it can decode message A. So we'll see that we saved 1 transmission by using the network coding technique, right? And in addition, this network coding can allow us to exploit the broadcast properties of wireless spectrums, which is not utilized in the original transmission. So let's see that these methods can be generalized to the case that we have more than 1 intermediate node. So in this case, for example, that we have 2 relays. So unlike traditional method in which if we have a stream of packets in one direction, each packet needs to be broadcasted by each individual node without coding, and in opposite direction again it needs to be rebroadcasted by each individual relay. With network coding, each relay can just broadcast one packet per two packets that needs to go in opposite direction. So instead of transmitting two packets, each relay node can just broadcast one packet. So this way we have a advantage of sending 50% less packets than or reducing the number of transmitted packet by a factor of 2. Right? Again, instead of the relay node will just receive two packets from two incoming links, we'll combine them together, and instead of forwarding those two packets individually, we just mix them together and broadcast the combination of them. So instead of transmitting two packets without coding, we'll just transmit one packet with coding. So we'll see that we have a pretty substantial gain by using this. So to utilize this, of course, it's called reverse carpooling because it's basically saying that if we can send packets in one direction, we can transmit packets in opposite direction for free. And again, we'll see the research problem here, right? Because to fully utilize the advantages of doing this, we need to make sure that we're sending those flows need to match each other, right? So if you're sending a lot of packets over one path, we need to have enough packets over sent over the opposite path to take advantage of this technique, right? So to make sure that we can actually code.